So we are actually going to post these lecture videos online. I think Nilesh has sent an email to you. So if you have any issues or concerns or so, please let us know. But this is lecture number 1. So let's get started. I am sharing my iPad window. So hopefully you can see my screen as I start writing. So this is lecture 1. And today I will be talking about, one of the very first topics in machine learning, which is linear regression. So as an example of a problem, right? So let's consider an example predictive problem, which is, let's suppose you want to predict levels of some particular PSA levels from various measurements on the prostate. Okay. So, it's not the details are not that important, but what is important is that there are two things. One is that there are some measurements on something that we want to do prediction on. So those we will represent by the xi. So we'll typically have training data, which will be x1, x2, x3, x4, and so on till xn. And along with every training data, which is the measurements, we'll actually have a label or a real number. Okay, so in regression, it will be a real number. And so we will denote that by the corresponding y. So y1 along with x1, y2 along with x2, y3 along with x3, y4 along with x4, and so on. Right? So if you have n amount, and this is known as the training data. So basically, we'll be given measurements and we'll be given the levels of PSA for n amount of training data. Okay, so just to clarify, the y1, y2 through yn are known. Okay, each yi in regression belongs to R, which means it's a real number. So this is regression. And later on, we'll see that we can have classification problems where these yi's may be, integer valued or are categorical variables. Okay, and again, reminding you that x1, x2, xn are measurements on the prostate. Okay, and typically they will be not just a single value, but they may be D features or D variables that you're going to base your prediction on. So typically, xi is going to belongs to RD. So this means that x1 is a D-dimensional vector, x2 is a D-dimensional vector, and so on. So all the xi's are D-dimensional vectors. So that basically says that you have D measurements on the prostate. Okay. Let me talk a little bit about another interesting example, right? Which is, let's suppose you are on Netflix. Okay. So this is kind of the recommender system problem, right? And there is a user, there is a particular movie or a show, right? And there's a particular rating that this user has given to this movie. Okay. And so, for example, an X could be, an example of user and movie features which are for this user and for this movie. And then the rating is actually the label or the Y's, right? So, for example, X could be, let's see, it's me, Indrajit, and there are maybe features that are available to the prediction algorithm about me, right? And let's say a movie or the show might be, Breaking Bad, episode 1 of season 1. Okay. And then let's suppose I have given, uh, I actually ended up not knowing about this show surprisingly till COVID. So I actually watched all this during COVID times, and the first show was okay. And then of course I got hooked onto it. Right. So first show maybe I gave 4 stars. Okay. And so this would correspond to the yi, and like I said, this features correspond to the x. Okay. And the reason I mention it is there was actually a $1 million, $1 million Netflix prize about 20 years ago that Netflix actually sponsored, right? So what they said is that they are going to basically release, I forget how many ratings they released. Of course, they did not release any user features because of privacy, right? But they basically gave a movie, let's say a user ID and the rating of the movie. And they released maybe 20,000 ratings, and they had a held out data set. And they said whoever gets 10% better than their current system at the time would actually get $1 million. And this happened around, nearly 20 years ago. And it actually spurred a lot of research in this area, in machine learning, right? And especially on recommender systems. Now, in both the above cases, right, in example 1 and example 2, you're already given, for example, in example 1, you're already given measurements and you're given the level of PSA. In example 2, you're given a user movie pair and you're given the rating of this movie by this particular user, right? So what is the actual technical problem that we need to solve? What is the prediction problem that we need to solve? In both these cases, the goal is to predict y for a new x. Okay, so in particular, in the first case, you will be given a new d-dimensional vector, and then you need to predict the level of PSA. In the example 2, you will be given a user movie pair through its features. And then what you need to do is you need to predict what rating this user would give to this particular movie, right? And of course, the interesting cases are exactly those where this X is not in the training data, right? Otherwise, you can just look up. So it's not a lookup problem, but it is a prediction problem, right? So predict Y for a new X. And then when yi belongs to R, this is a regression problem. Okay. I mentioned a couple of times this yi equal to belongs to R or a real value. Well, what are cases where the yi's might not belong to a real value, right? So for example, spam prediction is a problem, right? So let me give you another example, which is not a regression problem, right? Which is predict whether an email is spam or not. Okay, and whether you know it or not, all the various platforms like Gmail, Yahoo Mail, and so on use some sort of spam filter because otherwise your email will be overrun by spam, right? So over here, what is the X? If I say capital X is the set of the XIs, right? So it's set of emails. Okay. And now remember that in many of these prediction problems, even though, in this class, maybe we'll not be looking into it, maybe you'll be looking into in the projects. We are just saying that, you are actually given a d-dimensional vector for practical problems, you may need to figure out exactly what are the features that you're going to use, right? So for example, you might end up using, the words that are in the email. You may want to tokenize that, or you may look at, maybe the sentiment or something else in that email, okay? And what is Y over here? Okay, so Y is not really a real number over here. You want to predict whether an email is spam, okay, or normal. Okay, so it's a categorical variable, right? So you need to predict whether it's spam or not spam. Now you might encode it, and you will, in most cases that we'll see, you will encode it using a real number. Like for example, you can have 0 for one class and Y equal to 1 for the other class, or you can have -1 for one class or Y equal to 1 for another class, right? But that's just an encoding. The nature of the problem is that Y is categorical. Okay, so when Y is categorical, then this is a classification problem. And then when Y is real valued, then this is a regression problem. Okay, and we are going to start off this class by talking about regression problems, right? And later on in the class, actually, the next topic after this will be classification problems. Okay. So now let's formulate this mathematically, see what it means to try to get a prediction algorithm, and let's look at how we might formulate it and then actually solve this prediction problem. Okay, so let me write this again. We are going to do regression problem. So what we are given is xi, yi. Xi belongs to Rd. So D real numbers. So think of xi as a vector, and yi belongs to R. So that's a regression problem. Okay, and then typically you're given 1 to n amount of training data. Okay, and now of course, in modern day times, n can be very, very large, right? But n can vary from tens to hundreds to millions. Okay, and when n starts becoming very large, we will also look at, how much time does it actually take to train such, to actually form the model. Okay, so let me just take x, which is a particular xi, and let me denote it by its D features, right? So it belongs to D, Rd. So x has D components, x1 through xd. Okay. So what could be the simplest model that you can try and get with these D features, right? So the simplest model that you can have is you can say, okay, I will take a linear combination of these features, and I need to figure out what linear combination to get so that it actually matches the training data, right? That's one very simple formulation of the problem, right? So let's formalize this formulation. So if I want to do prediction, and the simplest way of doing prediction is to linearly combine these different features, these D features. So given an X, I'll make a prediction Y. And I will say that my linear combinations, let me denote them by W's. So I have W naught plus W1 X1 plus W2 X2 plus WD XD. Okay, so this is just a linear combination of these D values in X, or like I've already called it multiple times, these are the D features of the problem. And now I can write it, and this is where we start seeing some linear algebra, which will make allow us to form the problem much more concisely, right? And be able to solve it also in a way concisely, right? So I'm going to write this as W naught plus an inner product between the vector of my coefficients times my vector x. So this is W bar transpose x, and W bar is W1, W2, WD. So W bar is a d-dimensional vector, right? And I can also, so now I have, two parts to it, right? I have W1, W naught plus W bar transpose X. I can actually I'm going to write it more simply as just W transpose X bar, okay? Because I can write this as W naught times 1 plus W bar transpose X. So I can basically form one bigger dimensional vector X bar, which is X is going to be, its first component is going to be 1, and the rest of the components are going to be as they were before. So X1, X2, X. Okay. And like and W is going to be equal to W naught, W1, W2, WD. And I've written them next to each other, right? So the definition of an inner product in linear algebra is that you basically take the corresponding coordinates and you add them up, right? So it's W naught plus W1. I guess maybe I should use a cursor. Let's see. You guys can see a cursor here, or yeah. So you can see, I can take 1 times W naught, okay, W1 times X1, and so on, right? And WI, W and X both are now D plus 1 dimensional vectors. Okay, W and X bar, sorry. Okay. So this is now my prediction. It is W transpose X bar. Okay. So what happens with W transpose X1 bar? Okay, let me just write this again so that you can see clearly. So I have W transpose X1 bar. Well, remember X1 is the first training data. And what was its corresponding label? Well, its corresponding label is Y1, right? But remember that this is the prediction. This prediction, we may not actually exactly want it to be X1 or Y1, right? So I'm going to call this as Y of X1. This is my prediction. The given label, the value that we wanted to take is Y1. Now, one question that you should think about is, do you want this to be exactly equal or not? Right? So think about the case where n is in the millions. Typically, my d will be fixed. So let's say d is in the, let's say 10, right? And n is in the millions. Then I only have 10 or 11 parameters, right? If I count W naught, then it's 11 parameters, right? And I have million values to predict. So there is no way typically that you will be able to get exact equality, right? And in many cases, it may actually not be good to actually have exact equality, because that leads to a phenomena in machine learning called overfitting. And you don't want to do that. You don't want to necessarily predict the existing labels in the training data perfectly, but you want to do a good prediction of new data points that come. Okay, so we will not do this, but we want to try to fit it well. So I'm just going to say that this should be approximately equal. Okay, so similarly, I have the prediction for x2, which is W transpose x2 bar. I want it to be y2. And then I have y of x3, W transpose, W bar, well, sorry, too many bars. So I have W transpose, sorry, is W transpose x3 bar to be y3. And similarly, I have y of xn, which is W transpose xn bar equal to y. Okay. So now what does this mean? What does this nearly equal to symbol mean? Okay. Which means if I look at the prediction, my prediction is W transpose x1 bar, right? My actual value is y1. So I need some measure of error between y1 and W transpose x1. So the simplest thing to do is to look at the squared error. So I want this to be small. So W transpose x1 bar is the prediction. Y1 is the corresponding label. And I want the prediction to be close to Y1. I don't necessarily want it to be equal to Y1 for the various reasons I've mentioned before, but I want them to be close, okay? Similarly, I have the prediction for the second training data is W transpose x2 bar minus y2 square is small. I have W transpose x3 bar minus y3 square is small, and so on. W transpose xn bar minus yn square is small. So that is kind of the what I desire, right? So now I have n error estimates, right? And I need to somehow make them small. So what I can do is I can basically take the sum of all these squares. And I can say that I will, make the either sum or the average of these values to be small. So I can take, summation of, so this is a summation sign, I equals 1 through n, W transpose x I bar minus yi. Okay. I want this to be small. And for convenience, because we'll see when we take the derivatives, I'm just going to do 1 divided by 2. And I'm going to call this as a function of my coefficients. Okay. So this is FW, and what do I want to do? Right? This is a measure. So given the particular W, this gives a measure of the error on the training data. And in particular, this is the least squares error on the training data. Okay. So one goal, what do we want to do? We want to make this small, right? Like I've written above, right? The one goal is to find the W such that I minimize f of W. And this is called least squares regression. Okay, let me take a little pause and see if there are any questions so far. By the way, you should feel free to kind of, ask questions, feel free to raise your hand and interrupt me.
Question. Why is like when we are thinking about the distance, like the square error is the most natural one that comes up? Why don't we use, for example, absolute error?
great question. So one is it's actually going to make the computations much more simple. And they're actually going to be, we'll see that this has a closed form solution. But when we take something like absolute values, problem is a little bit more complicated. Many people would want to solve it, and there are algorithms to solve it. We're probably not actually going to touch upon it in this class. But, for example, the absolute value is, for example, not differentiable everywhere, right? So it leads to some complications. And so this is classical least squares regression. It's the first topic in this course. And we'll see that, it ends up having a simplified solution. Does that answer your question? Or?
Yes, thank you.
Okay. And then so I don't know if I always monitor the chat. So feel free to kind of remind me if there are questions on chat. So I do see a couple. So there's a half in front because, it's just a scalar. It doesn't really matter. But we'll see that when we take the derivative of, a square, a 2 comes out and it'll cancel out, right? So it's just a convenience. Another question, Prachi, which is, we can easily kind of have taken 1 divided by n. It doesn't really affect things. Okay. Okay, any more questions? Okay, so now we have a particular mathematical problem, right? We need to find the W that minimizes the sum squared error of the prediction from the true value. So how do we go about solving this problem? Okay, so this is where, for example, linear algebra comes in, and we'll see that with linear algebra, there are advantages. We'll be able to express the problem compactly. We'll be able to find pose the solution also very compactly, and we'll end up getting rid of these very kind of annoying indices. Otherwise, it can actually get overwhelming when you have to manipulate all these indices. I'm almost sure that I've probably made some error already in what I wrote, right? Because I had to manipulate the indices. Maybe I haven't, right? But it becomes cumbersome. So let's see how to express the problem in a very compact way using linear algebra. And then that'll also lead to a compact way to get the solution. Okay. So here's what we are going to do. We're going to take all the training data, and we are actually going to put it into a matrix. Okay. So I'm going to take my x1 bar, x2 bar, all the way up to xn bar. Okay. Remember that this is d+1 dimensional. Okay. So there are d+1 rows in this matrix. And obviously the column dimension is just n. Okay, so this matrix, I'm going to call it as X, right? So X belongs to d+1 by n. Okay, so there are n columns. The ith column is xi bar, and xi bar is d+1 dimensional. Its first coefficient, first column is, sorry, first element is 1. Okay, and the rest of them are the D features. Okay, so well, how does it, well, let's also do the same thing for Y, which are the labels. Okay, I'm going to say that Y is Y1 through Yn. So these are the n labels. And Y belongs to Rn. And I can actually just write out the X in more detail, right? Just so that you guys realize that it is a d+1, there are d+1 rows, right? So I can actually expand this out. So x1 bar is 1, x1 1, x1 2. Please keep me honest if I make a mistake. 1, x2 1, x2 2, x2n, And then I have 1 xn 1 xn2 xn. Okay, did I expand it correctly? Yeah, all good. Okay, somebody should have corrected me. I deliberately made a mistake, right?
Yeah, we have it d plus 1 by n, but now we have an n plus 1 by n something.
Yes, good catch. So this time I deliberately put this mistake. So I was just trying to see whether people are paying attention. But it's also my inbuilt excuse. Now I can actually make a mistake and just tell you that, I did it deliberately to see if you would catch it. I'm just kidding. But what I have over here is D, D, D. Okay, so remember X is D plus 1 by N. So each column of this matrix X is basically corresponds to the corresponding training data. Okay, Prachi also pointed out that I should make this correction. Feel free to interrupt me and or raise your hand or so, right? I don't always see the chat. I actually have it open right now, so that's good. Okay, so how do I use this? How do I use X, W, and Y? So now I have a matrix X. This I know is D plus 1 by N, D plus 1 by N. I have Y. Y is Rn. And then I have W, which belongs to Rd. Is it Rd? Rd plus 1. Right? So because I have W naught, W1 through Wd. Remember, my objective is this. So what I can do is I can actually write, if I think about my matrix X, right? I can think of my prediction X transpose W as taking an inner product between the column of X, right, and W. So what I can do is I can take a transpose of X and I can write X transpose W. So now think about it, right? What is X transpose W? X transpose is N by D plus 1, N by D plus 1, and my W is D plus 1 dimensional. So when I multiply the two, I basically get my prediction, right? I basically get a vector Y of all the X's, right? The first value is going to be W transpose X1. Second value will be W transpose X2, and so on. And now I need to match it up with the Y's, right? So there are X transpose W is an n-dimensional vector. And if I now subtract it from Y, right? And if I look at it, then each, if I look at f of W, then each term inside the sum is exactly equal to one element in this vector. Okay? And then in linear algebra, there's something called the norm of a vector. So if I take the L2 square norm, f of W is exactly that. Any question about this? So this is where I start using basically things that you should have learned in your linear algebra course, right? So a norm, the L2 norm of a vector is the square root of the sum of squares of the components of that vector, right? In this case, we don't need to take square root, right? So it is the squared L2 norm. Okay, so that's the same as so this is the least squares objective. So, any question? Everybody familiar with L2 norm? Okay, but this is identical. So what I've written over here is a very, very compact way of writing what was over here. They're exactly equal. Okay. So now, again, I haven't really done anything. I haven't really made any progress towards solving it, except that I've written things more compactly. Okay. So remember, the goal, as before, is to find W such that FW is minimized. So how would you do it? Well, just think about it, right? This is my W's are my coefficients of variables that I need to figure out, right? And it's quadratic in W. So what do? I take derivatives
Take the derivative and equals it to 0 and
and
solve
I
it.
set it to 0, right? So take
Yeah.
derivative and set it to equal to 0. Okay, so let's do that. Okay. Now remember that if I take a vector z, so a property of square norm is that it's basically the same as z transpose z. Okay. So I can write f of w is half of x transpose w minus y transpose times x transpose w minus y. Okay. Let me just do some manipulations. I have a transpose over here. I can write it as w transpose x minus y transpose times x transpose w minus y. Okay, and then I multiply the whole thing out, right? I get half of first term with the first term w transpose x, x transpose w, minus y transpose x transpose w, minus w transpose x y plus y transpose y. Okay. Another fact is that, if I take A transpose B, where A and B are two different vectors, that's exactly the same as B transpose A. Right? So I can write, so these are essentially transposes of each other, this and this. So I can write this as half of W transpose X, X transpose W, sorry, minus 2 Y transpose X transpose W plus Y transpose Y. Okay, so I've just expanded it so far. I haven't taken the derivative, but then that's the next step. I need to take the derivative, except that in this case, you have multiple variables, right? So I basically take what's called the gradient. So I take the gradient, and so this is notation for the gradient. So my variable that I'm trying to differentiate with respect to is W, right? So I'll basically have half of 2x transpose W minus 2 of xy. And this is why I had this half, right? It's basically this half will cancel out with the 2, and I'll get x transpose W minus xy. And then what do I need to do? I take the derivative and I set it equal to 0. Does that always lead to the minimum? Well, it always leads to minimum whenever it is a convex function, right? So in this case, it turns out that this is a convex function, right? And I basically take the derivative, I set it to 0, and my optimal W star is then going to be the minimizer of f of W.
I had a good question.
Yeah, go ahead.
In general, how can we know that f is a convex function?
One is if you have sum of squares, it's a convex function, right?
Mhm.
And in general, there's a test to see, like, for example, if it's a multivariate function, we can
Mhm.
look at the matrix of second derivatives. And if
Mhm.
that matrix is positive definite, then it's a convex function. Okay.
Oh, I see. I see. Thank you.
So remember that, for example, if you have just a scalar function, right? Test whether it's a minimizer or maximizer, you typically take the second derivative.
Right.
If the second derivative is greater than 0, then if you minimize, if you set the derivative equal to 0, then that's a minimizer,
Right.
right? So it's basically a generalization of this except to multiple variables.
Okay, I think that makes a lot of sense. Thank you.
Okay, good question. But again, this is the reason why we need you to have the linear algebra background. And Anas had a question, which was what W star was. This is my definition of W star, right? The W star is now the outcome of training this method. So if I take f of W, and if I find the minimizer of f of W, which is this. So actually, maybe I have conflated a few things. Sorry. I'll get better at this. Okay, so I set it equal to 0, right? But the gradient was just this, right? And so this is the value where gradient of W of f of W star equals 0. So basically my W star is this. Okay, so just to repeat, let me just see. Can you guys see a cursor here or no? No, right?
No.
No, no.
Okay, I need to figure that out, how to show you the cursor. Oh, you can see this, right? You can see the cursor now?
Yes.
Okay, somehow I see two cursors. Okay. But close enough, right? So this is the gradient. Okay, so if you take any W, then this is the gradient. What we want is that this should be set to 0 for us to get minimum of f of W. So my W star, which is, not very well written, this is W star, is the W, that particular W where the gradient equal to 0, which means this. Okay, does that make sense, Anas? Okay, great. Let's look a little bit closer at this, right? I want my, remember what X was? What was X? Let's see. How big was X? X was D plus 1 by N. Okay, X was D plus 1 by N. X transpose, well, how big is this? It's D plus 1 by D plus 1. What is W? W is D plus 1. Okay. So if you look closely at this equation, XX transpose is a D plus 1 by D plus 1 matrix. And there are D plus 1 unknowns. Okay. So this is D plus 1 linear equations. And I have D plus 1 unknowns. Perfect match, right? So that means that I can actually determine my W star uniquely. Although I haven't said a few things, right? When can I actually get a unique solution over here? Again, linear algebra comes in, right? I can write W star to be equal to, remember that XX transpose is a matrix, D plus 1 by D plus 1 matrix. And under certain conditions, it actually has an inverse. And so I can write my W in closed form as XX transpose inverse times XY. And this is okay if XX transpose is invertible or non-singular, or it does not have a zero eigenvalue, and different characterizations. Okay. Now it turns out that this is not the best way to solve the problem. If you're doing it on a computer, you don't actually want to take the inverse and after finding the inverse, multiply it by xy, right? The right thing to do is actually to solve this, okay? And these are called the normal equations. Okay? And we'll look towards the end of the class to see how we actually would want to solve the normal equations. Okay? So I have now given you a derivation. We've actually solved the problem, right? In some sense. As long as we know how to solve the normal equations, which I'll talk a little bit about, we now know how to solve the least squares regression problem. Okay, and what was the recipe? We looked at a loss function, which is the squared loss, and we basically minimized it over the training data that we are given. And how did we do that? We formulated it mathematically, and then we did some calculus and justified that we basically set the gradient equal to 0, right? And we got this. Let me give you another way of thinking about this problem, right? Which is a more of a geometric way and not as much algebraic, okay? This is actually the way I like to think about the problem. Okay, so let's talk a little bit about this geometric way. Okay. So remember that X transpose. Okay, so remember X was this matrix where each column was the training data with the one associated with it. So X transpose is 1, X1 transpose, 1, X2 transpose, 1, Xn transpose. Right? And if I write this as X bars, then I have X1 bar transpose, X2 bar transpose through Xn bar transpose. Okay, and remember my X transpose is Rn by t plus 1. And what I want is that my X transpose W is approximately equal to Y. Okay, what is X transpose W? Well, X transpose W is a linear combination of columns of X transpose. Okay, in particular, it is W naught times column 1 plus W1 times column 2 of this matrix all the way to WD times column D plus 1. I can actually think of it as in a geometric way, right? So I can basically say that, hey, this is a linear, these are linear combinations, right? And there are D plus 1 columns, right? So it's a subspace of kind of dimension D plus 1. So I can think of it as that, suppose I say that this is the column space of X transpose, which is also known as the range space of X transpose. If I take any linear combination, it'll give me some vector over here, X transpose W. There's some arbitrary W, right? But now Y is a particular vector. Okay, so remember Y is Rn. Okay, Y may not lie in this subspace. Okay, for Y to lie in this subspace, X transpose W must be equal to Y for some W. But it may not be the case, right? Because remember, we are not insisting on equality. So Y in general is not a vector in this column space of X transpose, but the optimal W star has the property that if I have X transpose W star, this Y, the way to get this W star is to actually drop a perpendicular onto this space. Because that perpendicular will kind of minimize, by Pythagoras theorem, will actually minimize the distance to this linear space. Okay. So what you can say is that, for W star to be an optimized, to be the optimal value, I should have the following, that X transpose W must be perpendicular to, and remember, what is this vector over here? This vector is Y minus X transpose W. So X transpose W must be perpendicular to Y minus X transpose W star for all W. Okay. And if that's the case, then it'll end up minimizing F of W. That means that W star would be argument of F of W. So remember, when are two vectors orthogonal, right? So for A to be perpendicular to B, this means that A transpose B should be equal to 0. So if I say that, I have X transpose W transpose times y minus x transpose w star to be equal to 0 for all w. And if I then, do a little bit of algebra, I have w transpose x, y minus x transpose w star equal to 0 for all w. And I have w transpose xy minus x transpose w star equal to 0 for all w. And since this is supposed to be true for all w, that means that this, right, this quantity should be equal to 0, which means that x transpose w star must be equal to xy. So I did not do any calculus over here, right? Just use kind of Pythagoras theorem, some intuition about linear spaces and so on, but I got the same solution. Same solution as over here. So just trying to give you a geometric interpretation of what this W star is, right? So it is the coefficients or the vector such that the residual y minus x transpose W star is actually orthogonal to that entire space, okay? So that's a different way of deriving it, okay? So, but remember, finally, we get the same normal equations. Okay, we get this again. So not a surprise, right? We are solving the same problem. We get the same solution, but this one was derived from a geometric viewpoint. And again, reminding you, I have d plus 1 equations because XX transpose is a d plus 1 by d plus 1 matrix. And I have d plus 1 unknowns. And this has a unique solution as long as XX transpose is a non-singular matrix. That may not always be the case, right? It's not guaranteed that XX transpose may be a non-singular matrix. So for example, suppose a feature is repeated, right? Which means that if I look at the matrix X, 2 rows are exactly identical. In this case, there will be linear dependence. The rank of the matrix will be lower. XX transpose will not be singular, and there will not be a unique solution. In fact, there will be an infinite number of solutions. Okay, but in the generic case, when you don't have linear dependence, okay, among the different features, right, we will get a unique solution. So what we need to do is solve x transpose times w star equals xy. This is a linear system of equations. I'm sure that all of you have studied this since all of you have taken a linear algebra course, right? So how do I solve this? Any volunteers? D plus 1 linear equations. XX transpose is a D plus 1 by D plus 1 matrix. And there are D plus 1 unknowns. Okay, so I'm sure that all of you have looked at how to solve such linear systems of equations. So the first method is to do Gaussian elimination. To solve x transpose w star equals xy. Now remember, these are prediction problems. I said n could be in the millions. D could also actually be quite quite large, right? So we need to quantify how expensive this is, which means that how much time or how many operations does it take to solve this? Okay, so what do we need to do? Well, to do this, you first need to form the matrix XX transpose. Okay, let me call that matrix as A. How many operations does that take? Well, it's a D plus 1 by N matrix, and I'm multiplying it, right? You can convince yourself that that'll take order D square N operations. Order D square N floating point operations. Then I need to form the right-hand side, which is this, right? I've already formed this. I need to form the right-hand side, right? And let me call this xy equal to b. Okay. Now this is not very expensive, right? This is all x is d by n. This only takes order dn operations. So that's not expensive. Now I have A, I formed A, which is XX transpose. I have W star, which I need to solve for, and I have the right-hand side. So now this is in the form where, you've learned in your linear algebra course how to kind of solve this, right? And what does Gaussian elimination mean? That you take A, you factorize it as L times U. Okay, you do this decomposition. L is a unit lower triangular matrix. U is an upper triangular matrix. And this is also called Gaussian elimination or LU decomposition. In this case, we are actually in a slightly special case, right? Because my matrix has this form, A is equal to XX transpose. So this is what's called a positive semi-definite matrix. Oh, my handwriting just goes haywire sometimes. Okay. I think it's when I try to hurry up. Okay, so it's a positive semi-definite matrix. When it's non-singular, it's a positive definite matrix, but it could be singular, right? And in this case, I can actually write LU decomposition as what's called Cholesky decomposition. Okay, where U basically is L transpose. Okay, and so let me just let you see what L is. L is lower triangular. U is, sorry, and of course L transpose then is upper triangle. So how does that help? How does Cholesky decomposition help? Well, if I factor LL transpose, by the way, this does take, to do this, takes a cubic number of operations. Cubic in the dimension. But once I have LL transpose, I need to solve for W star. I can do it in 2 steps. I can solve for L of Z equal to B, and then L transpose W star equals Z. Okay, and just think about what this is. This is L is a lower triangular matrix. Z is a vector. B is a vector, right? So the way I can solve it is basically the first equation I can solve for the first variable. Then I can solve using the second equation and so on. And this is called forward substitution. Okay, and this is actually not too expensive. It's only order d square. You can convince yourself, right? Because you're basically just making one pass through this matrix. And then when I come over here, then I get that L transpose is an upper triangular matrix. And I can basically use the last equation to get this W star D. Then I know W star D. I can use the second last equation to get W star D minus 1, and so on. So this is called backward substitution because I'm substituting backwards. So I get order D square again. Okay. So I can solve my normal equations by Gaussian elimination. In particular, Koleski decomposition, followed by forward substitution, followed by backward substitution, right? And I can solve it in order d square n, which was to form the matrix, plus dq. The d square operations get subsumed by dq. Okay. Okay. So I've gone pretty quickly, right? And the reason I've gone pretty quickly in the last 15 minutes is because you've all told me that you've taken linear algebra, right? It's a prerequisite for the course. And so there's stuff that you already know. So any questions or comments about that? So typically when I have taught this course for 25 years, typically what ends up happening is when I ask students, have you all taken linear algebra course? Everybody's hand goes up, right? And then when I get into the details, everybody kind of starts saying, oh, I don't really remember things, right? So what I will do is I will do a review of linear algebra next time, but it'll be a very, very quick review, right? So there are things like, what are the positive definite matrix? What are the eigenvalues? What is the SVD of the matrix? And I'm going to assume that you know that, right? It's not that the course is totally reliant on that, but it's stuff that, is very helpful to know when you're doing machine learning, especially if you want to understand the theory or the mathematics behind many of the things that come up. Okay. So again, like questions, comments, is this old hat? Should I not do the review? Should I do a review of the linear algebra part next time?
Review would be helpful.
Review would be helpful. Okay.
Okay.
Okay, good. So now I've given you only one way, by the way, of solving this problem, right? So I talked a little bit about, you get into trouble when the matrix is singular, A is singular, right? So, inverse of A or X, what is it, X transpose X or XX transpose? XX transpose exists only if A is non-singular. That means that's the only time there's a unique solution is when it is non-singular. But what happens if one feature is very close to another feature, right? There's something called the condition number of a matrix. Okay. So the condition number of A can be very large. Okay. And that's equivalent to saying if it is very large, then A is close to singularity. And then you get all sorts of problems with computing it on a computer, right? Even though the solution is exactly unique, you can run into kind of numerical issues, okay? It turns out that solving the normal equations is numerically not the best way of solving the problem, okay? So solving normal equations, which is what I gave you above, can yield large error when A is poorly conditioned, which means that the condition number is very large, okay? There are other methods of solving this problem, right? So remember the original problem was what? Minimize this, right? Minimize f of w, right? So there are other methods which are better when A is close to singular. Okay, one of them is to use QR decomposition of X, and the other is to use the singular value decomposition of X. Okay, and this is by far the best method. I don't know, I guess if I'm doing movie ratings, I would give it 5 stars. Okay, but it is expensive. It takes more computation to get the singular value decomposition. Okay, so this is the most accurate, but more expensive. Okay, so that leads us to the end of this particular lecture. There was I deliberately kind of made it a little fast paced. In the beginning, for 15-20 minutes, you would have been thinking, hey, why is professor going so slow, right? But I think I made up towards the end of class, right? And one of the reasons I want to impress upon it is there's a lot of linear algebra in machine learning. It'll really helps to understand what is going on. If you understand linear algebra, like I said, I will do a review, but I want to emphasize again that that is a prerequisite for this course, right? So if you do not have the prerequisite or you feel uncomfortable, please feel free to contact me or Nilesh. Okay, any questions before we conclude?
One question.
Yeah.
So if we have like d+1 data point, then the matrix would be d+1 by d+1, right?
You mean the X data? Yes.
Yes. So then solving it with these methods are going to give us like the exact like the overfitting scenario that you've talked about, right?
Yeah, I mean, it'll give you the exact, so yeah, it'll give you equality, yes.
Okay.
But generally in prediction problems, that's not what you're looking for, right? Because what could happen is that they're actually, I mean, by the way, this is not the way to solve a regression problem, right? I haven't talked about something called regularization, right?
Okay.
Which can actually lead to problems, right? So typically you want to also add regularization, and we'll talk a little bit about ridge regularization and lasso regularization, right? And so the goal is not to exactly make the training data set, the prediction be exactly this same for the training data. Because what could happen is then maybe one of the training data actually somehow there's an error in it, right? There's an outlier. And if you try to fit it too well, then you get into problems.
I was just pointing it out that
Yeah. No, yeah. That point is well made. Yes, you're right.
so therefore, basically, as you mentioned, we either bring in normalization or we have some sort of a lower bound for the number of data points that we have. Like if you have
Yeah.
not
I mean, you
enough
can
data
actually,
points, that might be
you can actually have prediction problems where there are very few data points and you are in very high dimensions. Right? In that case, the solution is not unique, but there are certain cases like in compressed sensing and so on, where you can actually get good solutions. So remember, I mean, this is the first course in machine learning. I'm not going to go into detail in lectures, but those are practical issues that come up in different prediction problems.
Thank you.
Okay, well, thank you for listening. Monday is a holiday, and so I will see you all next week on Wednesday. Okay, thank you.
Thank you.
Thanks.
Thank you.